Hey, good day, everybody. Today we're going to begin studying the key concept in statistics, and that concept is the idea of variation. So, this section 3.2 is about measures of variation. We're going to talk about three types of variation. We're going to talk about the range, very simple, very easy to find, the standard deviation, which let me put a star, this is the most important measure of variation for us. And then we'll briefly mention the variance as well. Sorry, my phone's beeping. Anyway, suppose we have two data sets that actually have the same mean. And so if you look at those two data sets, suppose one of those data sets, if you were to make like a dot plot or a histogram, that data set would look like this. All right, pretty bunched up over a range of numbers. And suppose the other data set and the mean here would be like 12.5. And the other data set would look somewhat similar in that in the sense that you would have data in various places and it would look something like this, and maybe the mean was still 12.5. And so what's the difference between these two data sets? Well, number one, the first thing we can see is this one's all clumped up. They're all sort of clumped together around the average. Whereas in this case, the data is more spread out and it could be spread out in various ways. But the data is not as close to the mean as we can see in the other sense. If you have that kind of situation, then you could say this one has a greater variance. Okay? It varies more from the mean than this other data set over here does. And in fact, we can show that very easily by the arithmetic we use to be able to find these numbers. So let's set about doing that part first. One of the important ideas of variation in business is that companies want to improve quality by reducing variation. Now, one of the things I always heard is McDonald's was very good at this. Now, whether you like McDonald's or not, and you have to remember McDonald's was a much younger corporation when I was a kid, and so it was like a highly new thing in those days. But one of the things McDonald's did very well is if you ate McDonald's in Colorado Springs, Colorado, where I grew up, or you ate McDonald's in Redding, California, or you ate McDonald's in New York City or in Miami, Florida, the quality of the food was the same no matter what store you went to. McDonald's worked very hard at that early on in their existence. And so I can never say that I, quote, got a bad Big Mac or a bad batch of fries, in the sense that if I got fries in Colorado Springs, or in my case in Pueblo or in Denver or in Woodland Park or any of the places I could go to a McDonald's, they were always the same fries. All right. and very always the same thing. And then when I moved to college and was in Oklahoma City, McDonald's fries were the same fries. And so in business, we can think of variation as something that we want to make small, all right? And if there's less variation, then you have sort of a total product, a good total product type of thing. Okay, so that's something really important to think about. Also, when we round off data, after we do calculations, we always do one more decimal place than the data. So keep that in mind. All right. So the first measure of variation that we want to deal with is the range. How do you find the range? Well, this is also the easiest calculation. You just take the maximum value in a set of data and you subtract the minimum value. And that will give you the range. Now, it's a very simple number. If you had two sets of data with the same mean, say you were measuring the number of French fries in a small order of French fries, all right? And you were doing this for different restaurants. And if you looked at those bag of fries and your maximum and minimum are far apart, then you would have like a large range and your quality control's not good because you're getting different amounts of fries in every bag. And so one thing you would improve is you might make a scooper that would give you the same amount of fries, or you would train employees to pay more attention to how they use the scooper and to make sure they were filling the bags, et cetera, et cetera. And so thereby you would have a smaller range from max to minimum. So all you do is do that subtraction to find that number. Okay? The range is not resistant. In other words, extreme values will affect its value. Okay? So suppose by accident you were measuring small bags of fries, and this could be a case that would happen, and somebody measured a large bag of fries. Well, your maximum would be way larger in that case. Maybe all your small bags of fries are really good here, but in the measuring, somebody had measured a max bag and it had a lot more fries, and then it caused your training to happen, and then you realized you just made a mistake in the data. So this would be a case where I would throw out this data. But that's just a typical thing. It's not resistant. This big value would make for a bigger range, and so you want to watch out for that. Okay? Now, let's go to standard deviation. So the standard deviation is a number that measures how much one piece of data deviates from the mean. So let's say in a bag of French fries, the mean of a sample mean of a bag of French fries is 75 fries. Okay? And then suppose we say that the standard deviation is 2 French fries. Okay? Then that's pretty small standard deviation. Then what happens is we can start to say, oh, my bag of fries has too many fries, when I start to get 2 or 3 standard deviations away from the mean. Okay? And so if I get a bag of fries with 80 fries, now I'm 2.5 standard deviations away. And I start to wonder, gosh, if I got a lot of bags that had 75 fries, what's going on? And I would start to, think there is a problem with my quality control in filling bags of fries. Okay. Another way to think about this is suppose that the test average on a test is 75. Okay. And suppose the standard deviation is 10. Okay. Then as a teacher, if I go one standard deviation above or one standard deviation below, I get a range from 65 to 85. I get a range of values. And I would kind of consider these the average values. All right. That group, they're fairly close to the mean of 75. So I would consider that average test values. Now, some people would be less, some people would be a little bit more. But then if I started being more than one standard deviation or two standard deviations away, so more than two would be like above a 95 on a test. Well, then that's telling me somebody's doing really well. Okay? I mean, really, really well. They're almost getting perfect if they were above a 95. And so this is sort of a way you can think about a standard deviation. Now, what it does is it kind of measures the average deviation from a mean. Okay? So if you have a set of data, right? Data is frequencies, and then you have a mean, X bar equals 75. So I've got all these test scores from students. I'm trying to find, in some sense, how far does each one deviate on average from the mean. Okay? Now, how do we figure that out? So let's go ahead and let's talk about how to figure that out. Okay, let's suppose I have 5 tests. 5 people in class and 5 people took the test. So I have my data, test scores, okay? And I'm going to make them such that their mean is 75. So I get a 75, somebody gets an 80, somebody gets 67, somebody gets a 77, or let me go 78, and somebody else gets a 75. Okay? So there's my data. Now, I want to find the average of that data. So let me list the data like this. Here's how you would sort of do it. So you'd have 75, 80, 67, 78, and 75. So this is the data, okay? And then down here, I can put n equals 5, all right? So then I want to find the average of that data. So let me find that X bar, the average. So I add these up. 75 and 75 is 150, 80 and 78, and 67 is 225. And so we end up with 375 divided by 5. And we get our average of 75, okay? Then what I want to do is I want to find the deviation. So what's the deviation? That is going to be the mean minus a data value, okay? And sometimes I label these data values like x sub I. So when I is 1, that means the first data value. When I is 2, that means the second data value, etc. So what this is the deviation, okay? Deviation. So I take 75 minus 75, I get 0. 80 minus 75, I get 5. 67 minus 75, I get negative 8. 78 minus 75, I get 3, and 75 minus 75, I get 0. And so I want to find the standard deviation. It feels like I want to find the average deviation. But if I just try to find the average of these numbers, look what happens. When I add them up, I get 0 plus 5 plus negative 8 plus 3 plus 0. I get 0. And so that's a horrible thing. By getting 0, I can't find the average deviation. And so that disturbs us. So what do? Mathematically, what we do is we do a little trick, is we take these deviations and we square them. And then what we'll do is we'll take a square root, which will get us back to the original form of the data. So then I have 0 squared, which is 0, 5 squared, which is 25, negative 8 squared, which is 64, 3 squared, which is 9, and 0 squared, which is 0. So what this does is it makes all the numbers positive. Then what we do is we add those numbers up. The sum of the deviations squared. Well, if I add those up, I get 64 plus 9 is 73 plus 25 is 98. So I get 98. Okay. Then what do I do with that? Then what I do is I divide this by n minus 1. Okay? Now, you would think you would divide by n, which is what we do if we're doing a population. But if we're doing a sample, we actually divide by n minus 1, and statistics theory shows us that this makes this number unbiased. In other words, it won't always underestimate what it should be. It'll tend to sometimes underestimate, sometimes overestimate, which brings balance to the statistical force, I guess. So we would divide this by 5 minus 1, or 4. Okay? And that would give us the number 98 divided by 4 is 24.5. All right? And then what we do is we take the square root of that whole thing. Okay? Which gets us back to the original form of the data. So the square root of that, which is really the square root of 24.5. And the square root of 24.5 is just a little bit less than 5, because square root of 25 is 5. So I'm punching that out on my calculator. Right now, I'm trying to find the square root. And wrong calculator. I apologize. So let me go to a calculator I like to use if my phone calculator is not scientific, which it is. It's not a scientific calculator. So calculator I like to use for this is pause. And so finally had a little problems with my internet. Now I can do this. Square root of 24.5. Whoops. Of course, I bunged that up, Mr. Fat Fingers. Sorry about that. I do clunky. And it's about 4.95. That would be our standard deviation. And I would, yeah. So I had 2 significant figures here, so I'd probably write 3 here. That's kind of that one more decimal place. If you want, you could round it Actually, you might want to just round it to 4.9 for the standard deviation, because that's one more decimal place. These digits are in the ones, so you need one more decimal place, which would be the tenths. So this would probably be the correct answer in the back of a book. Okay, so that's how I would do the standard deviation. So I find the deviations. This is step one. Let me put that in a different color. Let's go with this. This is step one. Put the deviations, which is actually, I'm sorry, let me do this. Step one is find the mean. Step two is then find the deviations, the mean minus each data value. Step three is then square each of those values. And then step four is add those values up, the squared deviations, add them up. Step five is divide that by one less than the sample size. And step six is take the square root. So I would never do this procedure unless I was doing it with a small amount of data, like no more than 5 pieces of data. Otherwise, I would just use technology. So let's review the technology we talked about today in class. So in class, if I had this data, I would do stat, edit, and then I would enter data in list one. So in other words, I make a little table with the data. Once I do that, then I'd go to the home screen, and then I'd go stat, calculate one variable statistics. All right. And then once I do that, I probably have to press enter here. Then once I do that, tell it that the data's in list one and the frequency is 1, then I would get the standard deviation is equal to 4.9. Okay? And that's how you would do that, and I remind you how to do that. Now, the standard deviation is what's called has a couple of properties that we think are fairly important. Okay? And those properties are things we need to know. Is that number one, they measure the deviation away from the mean. So in that sense, it's a standard measurement for that. It's never negative, so it's always a positive number. So that'll let you know if you've entered something wrong on a calculator or something like that. It's always a positive number. And it's only equal to 0 when all data are the same value. Okay? And so you want to keep those things in mind. Number 3, the larger means more variation. Smaller means less variation. And that should be relative to the number size. You know, if the numbers in our data are in the millions, we might expect the deviation to be, if it was big, in the 100,000s, and if it was small, in the thousands. But if our data are single digits or two-digit numbers, then a large one might be 10 or 15 and a small one might be 2 or 3. Okay? So it's related, larger or smaller is related to the size of the data values. Okay? Outliers affect the data. So an outlier is going to be a data value that's different from the typical data values you're looking at. So you got something that's really low or something that's really high. And that particular value, its deviation is because you're averaging all the squared deviations, it's going to affect the standard deviation a lot. And so outliers really affect it, make it much bigger. Okay. The units of the standard deviation, because we squared it and then took the square root, we're in the same units. So the units are the same as data. That's a key thing to remember. Okay. The other thing they talk about is they talk about the sample standard deviation as being a biased estimator. And what that means that it's a biased estimator of the population standard deviation. It means the values of the sample standard deviation do not center around the population standard deviation. So they'll tend to always be larger or always be lower if you have samples of the same size and so forth. And so they don't occur normally. They occur quite in a different pattern. So that's a theoretical thing. It's just something to think about. Okay? So at this point, we want to be able to find standard deviation for problems. So let's talk about that for a moment. So first off, the formula for sample standard deviation is equal to this, the square root of the sum of each minus sample data squared, so the sum of the squares, divided by n minus 1. And that's the original formula for standard deviation. Turns out there's a shortcut formula. And the shortcut formula is why the sum of the x squared and the sum of the x's show up on your calculator for one variable statistics. So I would encourage you to use those off your calculator to calculate the standard deviation and get the same number that the calculator is showing you. So this is actually a good shortcut. And this formula looks like this. The sample standard deviation is equal to n times the sum of the x squareds minus the sum of the x's squared. All right? And you divide that times by n times n minus 1 and take the square root of that whole thing to get to the same units. All right? And that will give you the standard deviation in exactly the same way. Now, the key is you got to make sure you put these things in the calculator correctly as an order of operations sort of problem. So on the TI, basically, let me show you what that would look like for the problem we just did. I'll set that up. Okay, I'm back. So What I did is I took the data from our example problem where we had the data values 75, 75, 80, 67, and 78. All right. And we had found that the standard deviation was equal to 4.9 using the round off rule and by doing the long formula. And so what I wanted to show you is the calculator gives me that value right here, 4.9. And we can use the other formula right here. And so I want to write that just to show you. You have to get these numbers from the calculator. So it's sort of redundant, but it's worth looking at just to see it. So we see how it can be computed. So n is 5 because there were 5 data values. And then you can see the sum of the x's and the sum of the x squareds right there. So the sum of the x squareds is 28,223 plus the sum of the x's, 375 squared. All right. That is all going to be divided by 5 times 4. N times n minus 1. So that's what the formula would look like. So now I want to punch that in a calculator and show you what the calculation would look like. So let me do that. And so here's our calculator calculation. So what I want to show you is that when I write something like this right here, I got to write it following the order of operations. So that's why I make sure I write this correctly. And then I know I need a parentheses around the whole numerator. And then I need a parentheses set around the denominator because I divide the whole numerator by the whole denominator. If you don't have the parentheses there, you're not going to get the correct answer. Okay? And so I'll let you do that and punch equals on your own. So if you'd have done that, you'd have got the wrong answer here. You'd have got the 118. You go, well, why has that happened? And this happens a lot. Sometimes you enter things in the calculator and you're trying to figure out what happens. One of the first things I always check is if I copied the formula correctly. And as you can see, I put a plus instead of a minus. So I should have a minus there. And so you got to watch out for stuff like that. Not only the order of operations, but otherwise. But given that, you can see you can actually show a calculation for the standard deviation if you're asked. So that's kind of a fun thing. Okay, let's go to the next slide. Sometimes what you want is just an estimate of the standard deviation. And so the quickest estimate is called the range rule of thumb. And all you need to do is take the range and divide it by 4, and that's approximately equal to the standard deviation. Now, sometimes it's not very close, but it does give you a quick approximation that you can use, okay? And so, given that, if I say the average height of a person who plays, of a male who plays basketball is 77 inches, let's say, 6'5", all right, 77 inches, then I want to know if this is the mean, all right. I want to know if somebody else's height is going to be significantly high or significantly low. And suppose our range of values for the basketball players in our sample, suppose they went from, say, 5'10", which would be 70 inches, up to 80 inches. Okay? And so the range would be 80 minus 70, or 10. And the range rule of thumb, our estimate for the standard deviation, would be 10 divided by 4, or 2.5 inches. Okay? Now, once I get that piece of info, okay, this is an estimate, an approximation, I can use it to kind of think about the differences. And so one of the things we want to look at really quickly is something going to be significantly low, high, or not significant? All right. And the way we can tell that is something is significantly low if it's more than 2 standard deviations below the mean. And high is going to be more than 2 standard deviations above the mean. And the values not being significant means they're going to be within 2 standard deviations. Okay? So let's watch how this would work for our silly little basketball example here. So we know the average height is equal to 77 inches. We know the standard deviation of our sample is 2.5 inches. Okay? We also know that, say we get a new basketball player, a transfer comes in, and suppose this transfer is 6'11", okay? So they're 6 feet 11 inches, which is equal to 83 inches. Okay? They're 83 inches tall. And I want to know, are they significantly lower, higher, or not significant compared to the rest of the players? So what I do is I take the average and I take the 77 and I subtract 2 standard deviations. I take the 77 and I add 2 standard deviations. Now, what this gives me is a number. 2 times 2.5 is 5. So this will be 82 inches, and this one will be 72 inches. And so a player who comes in off the street and wants to play, let's say, is going to be significantly above the average height of my team if they're taller than 82 inches. Or they're going to be significantly shorter than the rest of my team if they're below 72 inches. Okay? And then their height won't be significant if they're somewhere in between here. Now, somebody who comes in who's 6'11", if they can actually move their feet and shoot, then it's also significant because they have some skills. But 6'11" with skills is really nice in basketball. Now, 5'11" with skills is at 71 inches is okay, but they have skills, but it doesn't catch my attention as much because they're so far below the average height of the team. They just may not be big enough. Now, that's not always true in basketball, but that's sort of the idea. That's why people get impressed with size in basketball or football, etc. Okay? Now, so this is an interpretation. And all we did was use an approximation of the standard deviation. Now, you could also use the real standard deviation to determine significantly low or high or not significant. Okay? Next slide. Next slide. So, our third measure of variation is a number called the variance. What is the variance? Well, very simply, the variance is the standard deviation squared. Okay? And in this case, this is the sample variance, and then the population variance will be that value. And in fact, this is the symbol for variance. Now, there are lots of statistical methods that rely on variance, but there's one problem for us that causes an issue and will cause us not to really look at variance too often. And that issue is that the units are different. The nice thing on like the basketball problem, if I say the standard deviation is 2.5 for height, I know it's 2.5 inches. But if I said the variance is 6.25 inches squared, then it's not apparent to me how I can use that statistically to say something about height in inches. Okay? And so we tend not to use it as much just for that reason. And so we'll tend to focus on standard deviation a lot. And if we have time, we'll do something called analysis of variance, or what is called ANOVA methods. And if we have time, we'll take a look at those at the end of the semester. So at the end of your chapter is something called Beyond the Basics, or a section. And sometimes I do these and sometimes I don't. And this is a case where I'm going to talk about a couple of ideas. The first one is, we discuss it in class, why do we divide by n minus 1 in the sample and to find the sample standard deviation, and we divide by n to find the population standard deviation. And they basically talk in the book that this has a it's a theoretical thing. And so we don't worry about it too much. We just need to remember that. Now, how do we make sense of the standard deviation? Well, the way we make sense of a standard deviation is when we were talking about the range rule of thumb, and we started to say whether something is significant, not significant, or significant, not significant, or excuse me, that's not, well, yeah, that's correct. If it's significant higher or lower, significant high or significant low, and then not significant, that's the three categories. Oh my. That particular section, which is under the range rule of thumb, can generally be applied to the standard deviation, no matter how you compute it. And with that in mind, that leads us to a very important idea called the empirical rule. And the empirical rule is a way of thinking about how the standard deviation splits up bell-shaped data. So if you have data and you make a histogram out of that data, and when you look at the data, it has this sort of shape. Okay, so in a histogram, it's going to look something like this. Okay? If you have that sort of up and down shape, a bell curve kind of shape, then the empirical rule applies. And what the empirical rule says is, with a bell-shaped set of data, if you have a mean, okay, we'll call it X bar, and if we look at this on a number line, okay, so here's our mean. If we go one standard deviation above the mean, so X bar plus one standard deviation, and one standard deviation below the mean, then in between those is 68% of the data, okay? If we go two standard deviations above or two standard deviations below, then that means between those are 95% of the data, okay? And in fact, in these two little pieces here, you have 95 minus 68, or 27% of the data is between one standard deviation above and one standard deviation below. And so when you combine this with significant, high, low, not significant, you see why we say it's not significant if we're more than two standard deviations, because 95% of the data is below that. So now you're being significant, right? You've gotten something rare, and that's considered significant. So this empirical rule is an argument that we use all the time. Finally, just the last one, if you go three standard deviations above or below, that's 99.7% of the data. So if you ever find something that's more than three standard deviations away, that's a big deal. Okay? There's another thing called Chebyshev's that works with all it's like an empirical rule, but it doesn't have to be bell-shaped. All right? And basically it says within two standard deviations is 75% instead of 95. And within three standard deviations is 89% instead of 99.7. So these are good rules of thumb to keep in mind, the empirical rule and Chebyshev's, and you can use them. All right? So that is the lessons. Your job is, can you calculate a standard deviation on problems? In general, I'm looking at the problems. Try and do one problem the long way if it has up to 7 or 8 or 10 pieces of data at most. Or like number 10, where it has really simple differences. You might be able to pull that one off, even though it has a lot more data. But in general, I would focus on using the formula each time, or not the formula, the calculator each time to find your standard deviation, and then answer whatever questions they have about that. Okay? Alrighty. Good luck, and bring your questions to class. Talk to you later. Bye.